This is Group 1's final project presentation. As we all know, data scientists are in extremely high demand around the world. Companies are constantly fighting to acquire and keep talented professionals. However, as we've seen in the last year, many professionals are leaving their jobs and looking for new employment. Why is this? What are the factors behind it? And is this something that can be predicted? In this project, we utilized a data set from a Kaggle competition titled HR Analytics Job Changes of Data Scientists. This competition's focus is to determine which data scientists will be looking for a job change. The target variable is called target and is a binary 0 or 1, indicating whether the individual is looking to change jobs or they're not. To do this, we've been provided with a training data set with the following columns. We performed an extensive exploratory data analysis, including a clustering analysis, to get an understanding of the data, then performed data transformations and built models to see which were the most accurate in predicting which data scientists were looking to leave their jobs. The models we tested were Decision Tree, Random Forest, K-Nearest Neighbors, XGBoost, and SVM. In our data analysis, we noted that many of our features were factors. Only 2 of our columns were numeric. For our numeric features, we looked at the shape of our distribution as well as their relationship to our target variable. Based on our box plots, we can see that City Development Index has a strong relationship with our target variable, while training hours does not. For our categorical features, we looked at how many levels were in each factor and their percentage share of the factor. Additionally, to test the relationship between our categorical variables and our target variable, we explored the percentage of individuals who are looking for new jobs versus those who are not at each level of a factor. If we saw significant differences between the percentages at each level, we concluded that the factor and its associated levels were predictive of target. As you saw, there are very minor differences in almost all of the categorical features. However, we noted the following significant differences. Enrolled university, which is this one, experience, which is this one, and city. Next, we turn to missing data. Following our EDA, we determined that it was appropriate to drop company type, company size, gender, and major discipline, just based on the fact that there weren't significant relationship between these variables and our target variable. And these variables made up 98% of our missing values. After dropping these values, we used predictive mean matching to impute our nulls.
After that, we went ahead and did some unsupervised learning via k-means clustering to see if we could gain any additional insight into the data set. We chose k-means instead of hierarchical clustering because there was no obvious hierarchical standard to use on this. It didn't follow any particular category that we felt we should use hierarchical for, and k-means is a little bit easier computationally. Using k-means, we found an optimal number of clusters, which we found would be 3, which you can see in our cluster plot right down there, which uses PCA analysis to bring it down to 2 dimensions so that we can graph all of the variables in one graph. Those variables are broken up the second dimension is almost entirely based on training hours, while the first dimension is a mixture of our other variables, city development, experience, and last new job. Looking at these different groups, these different clusters, we found that some of the major differences between them existed between experience and last new job, where our 3 main groups were either lots of experience and a long time since their last job switch, medium amounts of experience and a short time since their last job switch, or little experience in a short time since their last job switch.
So with the EDA completed and all of our analysis of the data set done, we decided to start modeling. So the first model we tried was a decision tree here. And with all modeling, the first thing to do is to split the data for training and testing. With that, what I noticed was that the data was imbalance with about 14,000 zeros and just 5,000 ones. So this means that if our model was to just predict 0 all the way, it will still be 75% accurate. So to adjust for that, the first thing was to downsample so that we have an equal number of zeros and ones for the target. With that, we then created the decision tree model and then trained it. And you can see the confusion matrix here. So it shows that we have lower positive predictive value and higher negative predictive value. So our model is good at knowing at the zeros and a little bit at the ones, but not so much for the counter cases. So another model we tried was the random forest. So the random forest here was tuned, and the two tuning parameters was the mtry and min. It was the same data set that we used, the downsampled one. It was tuned across a grid of 30 of space 30. And it had to be done in parallel with 1,500 trees. So this took some time to actually train. So once it was completed, you can see how the distribution of how increasing the minimum node size affects the ROC AUC, which is the metric that was used to determine how good the model was. So with the tuning completed, we then created a final workflow, and we fit the original model with the new hyperparameters, and then trained it and tested it on the test set. And down at the bottom, you can see the confusion matrix now of how it performed relative to the decision tree. The random forest did a little bit better. It has higher positive predictive value, but slightly lower negative predictive value. And another thing to look at with the random forest was to see the feature importance. And this kind of goes in line with our EDA in that the city development index was an extremely important variable.
So following along after our decision tree and random forest, we looked at KNN, which is K nearest neighbors. And we started out by going through that data and just doing a little bit of pre-processing. We needed to center and scale, since KNN is highly susceptible to data that is on really different scale levels or widely ranging values. Then we went through and we split up into a training and test set, and we started to actually try to predict using KNN. We went through a training set where we went on different distances from 1 to up to Euclidean, and we tried both rectangular and triangular weightings and a whole bunch of different K values from 2 to 30. And you can see what we ended up with here in this distribution, or this graph. And we saw that our accuracy peaked around a K value of 27 and a rectangular weighting with a Euclidean distance of 2. And we ended up with an accuracy of 77%, but the sensitivity was incredibly low. You could probably do a better job guessing than what this model ended up with.
After that, we tried gradient boosting model. This model can have high variability and accuracy depending on their settings. And we have 4 tuning parameters that we're going to focus on. Is the number of trees. We tried 100 and 500, interaction depth, 6 and 9, and monopsonot, it's the minimum number of training set samples. We used 5 and 10. Also, the distribution time, we used ATA622 because this is a classification problem. So we tuned the model with the training set to find the best combination with the lowest RMSE error. So from the results over here, we can see the best combination for our parameters, and it's number of trees of 100, interaction depth 9, and monopsonot 10. We tried to increase the number of trees before, but it just affected our processing time, but not necessarily made any improvements on our model. So from the, can you scroll down a little bit? Yep. We can see that the accuracy metrics for our model, it's 77% and sensitivity is 58%. And city and experience are the most important variables in our model.
So the last model that we looked at was a support vector machine. So it's the idea of SVM is simple. The algorithm creates a line or a hyperplane which separates the data into the different classes. So over here, I use the same sample which we use for the decision tree and the random forest. And as we can see, the model consists of 4993 support vectors, of which there are two classes, 2511 with label 0 and 2482 with label 1. Now we'll try to tune this model a bit more. I had to run that offline. It took some time to do that. So we used 10-fold cross-validation for it. The best parameter that we could get was gamma of 0.5 and the cost of 1. Now we will get the best model using this and run it on the test data set. So that's the confusion matrix, finally what we have. So based on the result, we can see that the model is accurate in predicting someone who will not change a job, which is at 2692 true negatives. It doesn't do that good of a job for the other end, which is 762 for the false positive. Right, yep.
So as was mentioned, because we want to know how accurately our model predicted the data scientists that were actually looking to leave their jobs, we should focus on sensitivity as our metric. So in looking at our sensitivity from each of these models, we can see that all of the results are somewhat lackluster. So why did our modeling attempts fail? It's hard to say with certainty, but a large reason could be a lack of signal from our data set. We saw when performing our exploratory data analysis that very few features within the data set actually had any signal at all. It's quite possible that the few columns that did hold predictive power just didn't quite have enough signal for our model to detect. So in conclusion, based on our analysis and modeling, it appears that detecting which data scientists are planning to leave their jobs does not have a straightforward solution, at least with the present data set. This should intuitively make some sense. If companies were good at detecting who was going to leave, they could do more to incentivize them to stay, which is not what we've seen in the past year and a half. This problem will continue to stump analysts for years to come.